Okay, we have the basic exponential function which we graph. It's just the points, and when we initially graph it we don't sketch the curve. We'll sketch that later. The inverse of the basic exponential function is here. Now if you look at this table and this table, you see exactly what's going on. You see that the columns are reversed. And when you reverse the columns, you get a new set of points. Okay, so the points, well, they're obvious. 1/4 negative 2. So we graph 1/4 negative 2. Now I graphed 1/4 negative 4 because apparently my brain wasn't functional at the time. So actually my curve is somewhat wrong. So let me just quickly and somewhat sloppily repair this. It felt all right when I drew it, but we should have 1/4 negative 2. And then we have 1/2 negative 1. Now the curve is here. It actually makes a little more sense. Doesn't really affect what I did over here, which isn't all that accurate. Okay, so anyhow, there's the curve. So we do the points negative 1, 1/2 negative 1, 1, 0, 2, 1, 4, 2. We have to extend out here into our table for the basic exponential function, but there we have it. And then we are asked to estimate log base 2 of 3/2. Okay, and this function is called the base 2 log function, the log sub 2 of x function. That's the inverse to the 2 to the x function. If we had the inverse to the 3 to the x function, what do you think it would be? It would be log base 3 of x. Okay, but it's 2 to the x, so it's log base 2 to the x. Log base 2 of x. Okay, so here we have the points of our inverse function. Here we have the curve, and you're asked to estimate log base 2 of 3/2. Okay, well, people made their estimates. I got an estimate of 0.5. Somebody else gave me log base 2 of 3 minus 1, indicating clearly that that person already knows quite a bit about log functions. Now we're not going to study log functions, but we're going to maintain this graph as one of our basic functions. Now we've expanded our set of basic functions to include the inverse of the basic exponential function, and we're going to do inverses of other functions as well. Excuse me. Okay, so, here we've got it. And we estimate log base 2 of 3/2. Well, we locate 3/2. We come up to the curve, we come over here, and we estimate that that's about 0.4. Now somebody else estimated about 0.5. And then we had log base 2 of 3 minus 1. What would that be? Let's see, log base 2 of 3 is here. Looks like it's about 1.6. So that would give us something like 0.6 if that was a good estimate of log base 2 of 3. Now you can do these in your calculator. It's very easy. I'm not going to tell you how. We get to that in about a month. Estimate the solution of log base 2 of x equals 3/2. Well, that would be a y value. Here's our log base 2 values. Here are our x values. Y is 3/2. We look over here, we come down here, we get about 2.7. Now, the person that gave me exact result here said, well, it's 2 times the square root of 2. It's absolutely true. And 2 times the square root of 2 is 2.818. So our 2.7 isn't too far off. Okay. Now, prior to this, we did transformations of the basic reciprocal square function. F of x equals 1 over x squared. We sketched graphs of f of x minus 2, f of x minus 2, and negative 2 f of x, based on the values of the basic reciprocal square function. those values are graphed at the white x's. Well, that's not an x up there, but the white dot's an x's. So there, and there. Okay, the graph of f of x minus 2 is shifted 2 units to the right. So we take each of these points and we draw an arrow 2 units long to the right, and we arrive at the point of f of x minus 2. So this point goes to here, this point goes to here, this point goes to here. All these arrows have the same length. This point goes to here, this point goes to here, this point goes to here. Every time we start at a point of the basic exponential function and we shift 2 units to the right, we get these points. And later on we sketch the curves in. So you can see the curves, so we kind of give that away when we're doing this. Here's the curve for the basic extended reciprocal function, reciprocal square function. And here is the basic extended reciprocal square function, the curve, shifted 2 units to the right. And that would be f of x minus 2. And f of x minus 2 is 1 over x minus 2 quantity squared. If f of x is 1 over x squared, f of x minus 2 is a composite 1 over quantity x minus 2 squared. Okay, we did more with that here, and we'll do a little bit more with it. But let's see what we did for f of x minus 2. Now you see I've got this circled in purple, and I've got arrows, vertical arrows downward of length 2. Okay, so here's our basic arrow of length 2. It goes from 2 down to 0. Arrow of length 2 in the downward direction corresponding to shifting 2 units downward. We apply that arrow to the first white point and we get this point. We apply it to the second white point and we get this. We apply it to the third white point and we get this. So we get this point, and this point. Purple X's at the heads of purple arrows. It's kind of hard to see the head of this arrow because it's obliterated by everything else I've drawn there. And we shift this one down 2 units. We shift this point down 2 units. We shift this point down 2 units. Now don't do a video analysis of whether my vectors all have the right length or not. They don't. But you get the indication of how these work. Okay? Then we do negative 2 f of x. That's in some ways a little more complicated. The negative means we've got to flip things around the vertical axis. So I've done that with these red arrows. This point flips down to here. This point flips all the way down to here. This point that's all the way up here flips all the way down to here. So every one of these white points has been flipped about the x-axis. And I could draw that curve, and that curve, if I drew that in red, would be the curve of negative f of x. But it's negative 2 f of x. So, f of x is a y value. Negative 2 f of x means that we double the y values. Now the y value of a point is how far it is from the x-axis. And of course in what direction. So here's a point on negative f of x. This green arrow is double the length, not of the red arrow, but of an arrow from the x-axis down to this point. So the head of this arrow is twice as far from the x-axis as the head of this arrow. So it goes here. We do the same thing with this point. The tip of the red arrow is a point on the graph of negative f of x. We take the distance to the x-axis, not the length of the red arrow, the distance to the x-axis, and we draw a green arrow twice that long, and there's our point. Okay, similarly here, we take this distance to the x-axis and we double it, end up down here, and that's our green arrow. Then we did the same thing to this point, and this point. So we reflected about the x-axis and we doubled the length. And we got these points. Then, for this function, we sketched a green curve corresponding to the green circle, just like the yellow circle we did for this function. And the function with the purple circle, we connect the points with a smooth curve, and we end up with the graph of this. So the purple graph is f of x minus 2. The yellow graph is f of quantity x minus 2. And the green graph is negative 2 f of x. The white graph, of course, is our original reciprocal square function. Then we made a table for y equals f of x minus 2. And that table is confined to the points on f of x minus 2 that we got from the basic points of the reciprocal function. So that if we graph the points on this table, we're going to get this curve. If we tried to graph the f of x minus 2 equal 1 over x minus 2 quantity squared function using just the points negative 2 through 2, well, none of our graph would have gone beyond here, and we would have only gotten this, and we wouldn't have seen this behavior and the symmetry. It's a big deal because when you ask people to graph things by plugging in points, they do it uncritically. They just pick standard points, whatever standard points they want to use, and they graph it, and they tend to miss the important aspects of the function. Like they miss the vertex of a parabola, they miss the axis of symmetry for this graph, and so forth. So that's one reason that I want to start with the graph of the basic functions, just the point graph of the basic functions, and then we can do transformations. These points come about because we're just reading off the coordinates of these points. Of course, we have to figure out the coordinates of these points, and that was somewhat of a challenge. So we'll have an exercise on that. Anyhow, there's our scheme.